Hello and welcome back. Or maybe welcome for the very first time. Either way, I'm so glad you're here. Wherever you are right now, curled up in bed, lights dim the world outside growing a little quieter. You've chosen well tonight. This is a safe, soft place. And we have a beautiful journey ahead of us. Tonight we're going somewhere extraordinary. Somewhere 60,000 light years away. A dead star the size of a small city is spinning 700 times every single second. And it has been doing this without stopping, without slowing meaningfully, without missing a single beat for longer than the Earth has existed. And the pulse it sends out across the galaxy is so precise, so impossibly regular, that when scientists first detected it in 1967, they sat in stunned silence and seriously debated whether it might be a signal from an intelligent alien civilization. They were wrong about the aliens, but they were right about something far more profound the universe had been keeping perfect time all along. And we had only just learned how to listen. That is where we're going tonight, into the quiet, extraordinary world of pulsars. But before we drift any further, if these slow science-filled nights bring you some peace, some wonder, some gentle company in the dark, I'd love for you to tap the like button. It's a small thing, but it means a great deal. And if you'd like stories like this one to keep finding you on the nights when the mind won't settle and the room feels too quiet, a gentle press on subscribe, and maybe the little bell means the next journey will know exactly where you are, not for noise, just so the cosmos knows you're listening. All right, now truly let's begin. Close your eyes or let them rest soft and unfocused the way they do when the mind begins to wander towards sleep. Imagine you are lying on your back in an open field, no city nearby, no phone in your hand, just you and the sky above, and the kind of darkness that makes you feel simultaneously very small and somehow deeply strangely okay with that. The stars are out, hundreds of them, thousands. And in the silence, you start to wonder, is any of this actually still? Is anything out there truly at rest? The answer, and this is something that never stops being beautiful, is no. Nothing in the universe is truly at rest. The stars that look fixed are racing through the galaxy at hundreds of kilometers per second. The constellations we name and navigate by will be unrecognizable in 100,000 years. Even the ground beneath you is moving, carried on tectonic plates that drift like slow rafts on a restless planet. Motion is not the exception in this universe. Motion is the rule. And some of the most dramatic motion, some of the most breathtaking physics happens in objects so small and so dense and so far away that they remain almost entirely invisible to the naked eye. Pulsars are neutron stars, and to truly feel what that means, not just understand it intellectually, but feel it somewhere underneath the ribs, we have to begin not with what they are now, but with what they once were. Because pulsars are born from death. From the most spectacular, most catastrophic, most luminous death in the observable universe. When a star much more massive than our Sun, 8 times, 15 times, sometimes 20, or more times more massive, finally exhausts the nuclear fuel at its core, something happens that no earthly vocabulary is quite adequate to describe. The core collapses, not slowly, not gradually. In less than 1 second, less time than a single heartbeat, a ball of matter containing more mass than our entire sun falls inward, crushed by its own gravity past every known form of resistance. The electrons and protons that made up ordinary atoms are forced together, merging under unimaginable pressure into neutrons. The density becomes so extreme that a single cubic centimeter of this material would weigh here on Earth approximately 1 billion tons. 1 billion tons. In a cubic centimeter. In something smaller than a sugar cube. This is the kind of number that deserves a pause. Not because it's impressive in a distant academic way, but because it is genuinely difficult for a human brain shaped by millions of years of evolution on a planet where things fall at a comfortable rate and matter behaves in predictable ways to absorb. A teaspoon of neutron star material transported somehow to your kitchen table would sink through the table, through the floor, through the building, through the bedrock, and keep going. It would punch through the earth like a hot needle through tissue paper and come out the other side. And the rebound from that collapse, the shock wave that results when the infalling outer layers of the dying star slam into this suddenly incompressible core, that rebound triggers one of the most energetic events in the cosmos, a supernova, a stellar explosion so bright it can outshine an entire galaxy of 100 billion stars, sometimes for weeks or months at a time. In the year 1054, astronomers in China and Japan recorded a new star appearing in the sky bright enough to be visible in broad daylight. They called it a guest star. It remained visible to the naked eye for 23 days and at night for nearly 2 years. What they were seeing, though, they had no framework to understand. It was a star dying nearly 6,000 light years away, an event that had actually occurred 6,000 years before their records, its light only just reaching Earth in that moment. At the center of where that star exploded, there is today a structure called the Crab Nebula, a glowing, expanding cloud of gas and debris nearly 11 light-years across. And at the heart of the Crab Nebula, spinning 33 times every single second, is a pulsar, the leftover core of a star that died before the pyramids were built, still spinning, still pulsing, still broadcasting its heartbeat across the galaxy reliably every single time. Now, not every neutron star becomes a pulsar. What distinguishes a pulsar is a combination of two properties that the collapse amplifies to almost supernatural extremes: rotation speed and magnetic field strength. Consider rotation first. You may have seen a figure skater perform a spin, starting slowly with arms extended, then pulling them in and suddenly accelerating into a blur. This is conservation of angular momentum at work. The spinning object's total rotational energy is conserved, so when its radius decreases dramatically, its rotation rate increases dramatically. A large star spinning lazily over the course of weeks can, when compressed into a ball 20 kilometers across, end up rotating dozens or hundreds of times per second. The math is elegant. The result is dizzying. Some pulsars spin so fast that points on their equator move at a significant fraction of the speed of light. And if they were spinning just a bit faster, they would begin to tear themselves apart. Now, consider the magnetic field. Our sun has a magnetic field. It influences solar flares, coronal mass ejections, the aurora borealis visible on dark winter nights near Earth's poles. It is by human standards immense. But when a star's core collapses from something hundreds of thousands of kilometers across into something 20 kilometers across, the magnetic field lines are compressed along with everything else. They concentrate, they intensify. Some neutron stars end up with magnetic fields 1 trillion times stronger than the sun's. 1 trillion, the number that follows 1 billion. And the most extreme class of neutron star, called magnetars, have fields so powerful they can distort the shapes of atoms themselves, compressing the electrons in their atomic orbitals into elongated, narrow configurations, unlike anything that exists anywhere else in the universe. From the interaction of that extraordinary rotation and that extraordinary magnetic field, something remarkable emerges. Along the magnetic poles of the neutron star, which critically are not perfectly aligned with the rotational poles, just as Earth's magnetic north is offset slightly from geographic north, beams of radiation are generated and flung outward into space. Radio waves, X-rays, sometimes visible light. These beams sweep around with every rotation of the star, like the beams of a lighthouse sweeping across a dark sea. And if Earth happens to lie along the path of one of those sweeping beams, if we are positioned in just the right direction in space, then with every rotation, the beam sweeps past us. We detect a pulse, a clean, sharp, regular burst of radio energy arriving from across the galaxy. Once per rotation, like clockwork, like a heartbeat, steady, faithful, impossible to confuse with noise once you know what to listen for. Here is something that rewards quiet contemplation. That regularity is not simply impressive, It is not just a curiosity of physics. The best-timed pulsars, the millisecond pulsars, which we will come to later in tonight's journey, keep time with a stability that surpasses every clock human civilization has ever constructed. The atomic clocks that underpin the GPS satellites circling Earth above us right now drift by about 1 second every 300 million years. Some millisecond pulsars match or exceed that precision, powered by nothing but the physics of their own collapse broadcasting freely across the cosmos. They have been keeping time since before our solar system existed, and we found them by accident. We found the heartbeat of the cosmos, not because we were clever enough to go looking for it. We found it because a 24-year-old graduate student in Cambridge, England, was doing painstaking, unglamorous radio telescope work on a cold November night, and she noticed something that everyone around her said was probably just interference. She kept watching it. She kept recording it. She refused to look away, and the universe rewarded her attention with one of the greatest discoveries in the history of astronomy. That story, the story of Jocelyn Bell, the signal that was almost named after aliens and the Nobel Prize that went to the wrong person, is where we're going next. Because the discovery of pulsars is not just a story about science. It is a story about who gets to be taken seriously, who gets the credit, and what happens when the universe speaks, and only one person is paying close enough attention to hear it. In the autumn of 1967, at a radio telescope observatory outside Cambridge, England, a young woman named Jocelyn Bell was doing the least glamorous work in astronomy. She was reading chart paper, miles of it, literally miles. The radio telescope she worked with produced roughly 30 meters of paper chart data every single day, and her job as a first-year PhD student was to go through all of it by hand. No algorithms, no automated scanning software, just her eyes moving along columns of squiggles and lines, looking for anything unusual in the radio signals coming from deep space. It was painstaking, it was repetitive, and for most of the summer and early autumn, it was unremarkable. And then, in October 1967, something strange appeared in the data. It was a signal. A repeating regular rhythmic signal. Pulses of radio energy arriving from the same point in the sky, separated by exactly 1.3373 seconds. Not approximately, not roughly, exactly with a precision that made the signal impossible to explain as a natural random phenomenon. Because random things in the universe are not that regular. Noise is not that regular. Interference is not that regular. The only things in human experience that produce signals that regular are machines, clocks, transmitters, things that are built and operated with intention. Jocelyn Bell brought the signal to her supervisor, the astronomer Anthony Hewish, and what followed the weeks of doubt, the debates behind closed doors, the quiet, uncomfortable question that eventually had to be spoken aloud, is one of the most quietly extraordinary moments in the history of modern science. They called it LGM1, Little Green Men 1. They were only half joking. Think about what it would feel like to sit with that signal. You are a scientist. You believe in rational explanation. You have spent your career looking for natural phenomena, natural causes, natural processes. And here is a signal coming from a fixed point in the sky, meaning it moves with the stars, not with the Earth. So it is not a human-made transmitter repeating with mechanical precision. Every 1.3373 seconds without fail. What do you do with that? What do you write in your notebook? When the most parsimonious explanation, the simplest explanation, the explanation that fits the data most cleanly, is something out there is transmitting this deliberately. Bell herself has spoken about this period with characteristic understatement. She noted decades later that if it really was a signal from an alien civilization, it was rather inconsiderate of them to choose a frequency that overlapped with her PhD research. There was humor in it, but underneath the humor was something real, the genuine vertiginous moment when two scientists sat with data and could not rule out the possibility that they had just made first contact. Here is the common misconception worth addressing directly. Many people, when they hear this story, assume that Bell and Hewish must have been naive or credulous, or perhaps a little prone to wishful thinking. They were not. The LGM hypothesis was not a flight of fancy. It was the result of careful methodical elimination of alternatives. They checked for terrestrial interference. The signal was not terrestrial. They checked for reflections for instrument artifacts for known natural sources that could produce periodic radio emission. None fit. The signal was real. It was extraterrestrial. It was regular. And they had at that point no physical mechanism to explain how a natural object could produce something that precise, which is exactly the right response to unexplained data. Hold it carefully, don't dismiss it, don't overinterpret it, and keep looking. They kept looking. And in December 1967, Jocelyn Bell found a second signal, coming from a completely different part of the sky, with a different period, but the same kind of impossible regularity. Then a third, then a fourth. And at that point, the alien hypothesis quietly collapsed, not because anyone disproved it, but because the mathematics of probability became overwhelming. The idea that Earth had stumbled upon not one, but multiple independent alien civilizations, all broadcasting at similar radio frequencies, all pulsing with similar regularity, all invisible in visible light. That idea became far less plausible than what eventually emerged as the correct explanation. These were natural objects, objects that no one had predicted, no one had theorized, no one had expected. A new class of astronomical phenomenon discovered entirely by accident, by a graduate student reading chart paper by hand. The objects were announced to the world in February 1968 in a paper in the journal Nature. They were called Pulsars, a contraction of pulsating radio stars. The paper listed Anthony Hewish as the lead author. Jocelyn Bell was second author. This was in the conventions of the time, not unusual. A PhD student supervisor typically received top billing. But what happened 6 years later was unusual, and remains to this day a source of genuine discomfort in the scientific community. In 1974, the Nobel Prize in Physics was awarded for the discovery of pulsars. It went to Anthony Hewish and to Martin Ryle for a different contribution to radio astronomy. Jocelyn Bell Burnell, the person who actually found the signal, who actually noticed the anomaly in the chart paper, who actually identified multiple separate sources, and thereby transformed a curiosity into a discovery, received nothing. She was not mentioned in the Nobel citation. This decision sparked what became known as the Bell-Burnell controversy, a debate that reached beyond astronomy into questions about how science credits its contributors, who gets to be considered a discoverer, and whether the structure of academia in the 1960s and 1970s systematically undervalued the work of women and junior researchers. Many prominent scientists, including fellow Nobel laureates, argued that the omission was a serious injustice. Fred Hoyle, the distinguished British astronomer, stated publicly that Bell deserved to share the prize. Bell herself, in an act of dignity that many people find either admirable or heartbreaking, depending on their perspective, largely declined to pursue the controversy publicly. She went on to have an extraordinarily distinguished career. She became one of the most respected astronomers in the world. She served as president of both the Royal Astronomical Society and the Institute of Physics. In 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics, a prize that comes with a monetary award of $3 million, which she donated entirely to fund scholarships for underrepresented students in physics. The citation from the Breakthrough Prize Committee stated explicitly that the award was recognition of her discovery of pulsars and of her inspiring response to her omission from the Nobel. She was, in other words, finally and formally credited, 51 years after the discovery. There is a lesson here that extends beyond the history of astronomy. It is a lesson about attention, about the kind of attention that is not dramatic or headline worthy, the attention of someone sitting at a desk, going through chart paper day after day, resisting the very human temptation to ignore the anomaly because it didn't fit the expected pattern. Most scientific breakthroughs are not born from genius alone. They are born from that kind of attention. The willingness to look at something no one else thought was worth looking at, and to keep looking long after a less curious person would have moved on. Ask yourself, and this is worth sitting with. For a moment, how many times have you noticed something strange and talked yourself out of it? How many times have you had a question that felt too strange to ask, or seen something that didn't fit and quietly set it aside because it seemed easier? Jocelyn Bell could have set the signal aside. She could have marked it as interference and moved on. She didn't. And because she didn't, we know the universe has a heartbeat. Now the discovery of pulsars raised an immediate and urgent question that physicists set about answering with remarkable speed. The question was, what physically are these things? What kind of object could rotate fast enough to produce pulses separated by a little over a second, or in the case of later discoveries by fractions of a second, and do so with such extraordinary precision? The answer, when it came, required scientists to venture into some of the most extreme physics that nature allows. Because to understand a pulsar completely, you cannot just understand how it spins. You have to understand what it is made of. And the interior of a neutron star is even today one of the least understood environments in all of science. What lives inside a pulsar, what makes it tick, what keeps it stable, and what occasionally makes it suddenly lurch and speed up in ways that still surprise astronomers, that is the story waiting just ahead. There is a question that sits quietly underneath everything we have talked about so far. A question so fundamental that physicists spent decades wrestling with it before arriving at an answer that is, depending on your disposition, either deeply satisfying or deeply unsettling. The question is this: what exactly is the inside of a neutron star made of? We know what it looks like from the outside. We know how fast it spins. We know the shape and frequency of the beams it sends out. We can measure a pulsar's period to 12 decimal places from billions of miles away. But the interior, the core of the core, the place where pressure and density exceed anything reproducible in any laboratory on Earth, that remains even now one of the most genuinely unresolved questions in all of physics. And the story of how we have tried to answer it takes us into territory that blurs the boundary between the known and the imagined. Let's begin with what we do know. And to do that, we have to go backward, not just to the death of a star, but to its life. Because a pulsar does not begin as a pulsar. It begins as something almost unimaginably large, luminous, and alive. The stars that become neutron stars and pulsars are not like our sun. Our sun is a comfortable, middle-aged, medium-sized star. It will live for about 10 billion years total, and it is currently roughly halfway through that span. When it dies in about 5 billion years, it will expand into a red giant swallow, Mercury and Venus, and possibly Earth, and then gently shed its outer layers as a beautiful expanding shell of glowing gas called a planetary nebula. Its core will cool slowly into a white dwarf, a dense Earth-sized remnant that will fade over trillions of years into darkness. It will not explode. It will not collapse beyond the point of electron degeneracy. It will simply cool and dim and eventually go dark. But stars that are 8 or more times the mass of our sun live very different lives, and they die very different deaths. These stars burn hot and fast. A star 20 times the mass of the sun might live for only 8 to 10 million years compared to our sun's 10 billion. They are the mayflies of the stellar world, brilliant and brief. They shine with a luminosity hundreds of thousands of times greater than the sun. They burn through their hydrogen fuel at a ferocious rate, fusing heavier and heavier elements in their cores. Hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, oxygen to silicon, and finally silicon to iron. Iron is where everything stops. This is one of the most important facts in astrophysics, and it is worth pausing over. Every fusion reaction up to iron releases energy that is what keeps a star shining, what keeps the outward pressure of radiation in balance with the inward pull of gravity. But fusing iron absorbs energy rather than releasing it. Iron is the endpoint of stellar nucleosynthesis, the ash at the bottom of the cosmic furnace. When an iron core builds up at the center of a massive star, reaching roughly 4 times the mass of the Sun, a threshold known as the Chandrasekhar limit, the pressure can no longer support itself. The core is not producing energy. It is simply sitting there, growing heavier like a stone balanced on a pillar that is slowly being eaten away. And then the pillar gives way. What happens next occurs in stages so rapid that the word rapid feels inadequate. In the first few milliseconds, the iron core collapses inward at roughly 1/4 of the speed of light. In less than 1 second, often cited as around half a second, the core has compressed from something roughly the size of Earth to something roughly 20 kilometers across. The density becomes so extreme that even the fundamental particles begin to change. Electrons and protons, which normally keep a comfortable quantum mechanical distance from one another, are forced together by the pressure merging into neutrons and releasing ghostly particles called neutrinos in numbers almost too large to comprehend. In that fraction of a second, roughly 3 times 10 to the power of 53 joules of energy are released in the form of neutrinos. To put that number in some kind of context that is more energy than our sun will radiate across its entire 10 billion year lifetime multiplied by 10. Released in less than a second, mostly carried away by particles so small and so weakly interacting that the vast majority of them pass through the Earth as if it were not there. And indeed, neutrinos from supernovae have been detected here on Earth, arriving a few hours before the visible light of the explosion, because they escape the stellar interior so much more easily than photons do. The infalling outer layers of the star crash into this suddenly incompressible neutron core and rebound. The shock wave propagates outward, energized in part by the flood of neutrinos, depositing a tiny fraction of their enormous energy into the surrounding material. The outer star explodes. And what remains if the core mass stays below a certain threshold, roughly 2 to 3 solar masses, beyond which even neutron degeneracy pressure cannot resist gravity, and the core collapses further into a black hole, what remains is a neutron star. Now, here is where the story becomes genuinely strange, and where most popular accounts of pulsars and neutron stars stop short of what is most fascinating. The outer layers of a neutron star, a thin crust perhaps 1 kilometer thick, are composed of exotic but relatively understandable material, densely packed atomic nuclei, mostly iron and nickel, arranged in a crystalline lattice. Strange, certainly, impossibly dense by everyday standards, but recognizable as a form of matter we can model and test. Go deeper, and things become less certain. Beneath the crust, the density increases past the point where individual nuclei can maintain their identity. The nuclei dissolve into a sea of free neutrons with a small fraction of protons and electrons. Physicists believe this region may contain superfluid neutrons, neutrons that flow without any friction whatsoever. A quantum state that has no analog in everyday experience, but that has profound observable consequences, as we will discuss in a later part of tonight's journey. Go deeper still into the inner core of the most massive neutron stars, and physics enters territory where our equations begin to disagree with each other. Some models predict that at sufficient density, the neutrons themselves dissolve, that the quarks which make up neutrons and protons are squeezed so tightly together that they exist not bound inside particles, but free in a state called quark matter. Others predict even more exotic phases, strange quark matter incorporating the strange quark alongside up and down quarks. Some theorists have proposed the existence of color superconducting quark matter, a state in which quarks pair up in ways loosely analogous to how electrons pair in a superconductor, but governed by the strong nuclear force rather than electromagnetism. Here is the uncomfortable truth. that physicists will acknowledge openly. We do not know what the cores of the most massive neutron stars are made of. We have competing equations of state mathematical descriptions of how matter behaves at these densities, and we cannot yet discriminate definitively between them from observation. The interior of a neutron star is in a very real sense a laboratory that nature has built, but has not yet allowed us to look inside. This is not a failure of science, it is an invitation. And recent observations, particularly from the NICER telescope aboard the International Space Station, which has been measuring the X-ray emission of pulsars with extraordinary precision to try to determine their radii and thereby constrain their internal structure, have begun narrowing the possibilities. In 2021, NICER published measurements of the pulsar PSRJ0030 plus 0451 and PSRJ0740 plus 6620 that place new constraints on the neutron star equation of state, ruling out some of the more extreme proposed models. We are slowly learning to read the interior of an object we can never visit using only the light it sends us. There is something worth sitting with here, a reflection that goes a little beyond the physics. We live on a planet that formed from the remnants of earlier stars. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now. These elements were forged in stellar cores and scattered by stellar explosions across billions of years. You are in a very literal and non-metaphorical sense made of star stuff. But the heaviest elements, the gold and jewelry, the uranium and nuclear reactors, the rare earth elements in the device you might be listening to, those were not forged in ordinary stellar cores. Many of them were forged in the collisions of neutron stars. When two neutron stars spiral together and merge an event that produces both gravitational waves and an extraordinary explosion called a kilonova, the conditions for a fraction of a second recreate the densities and temperatures of a neutron star interior. And in that window, rapid neutron capture reactions build up heavy elements at a rate that no other known process can match. In August 2017, astronomers detected both gravitational waves and light from a neutron star merger for the first time, event GW170817, observed simultaneously by LIGO Virgo and dozens of telescopes around the world. The kilonova that followed was estimated to have produced a mass of gold and platinum equivalent to several times the mass of Earth. Every piece of gold that has ever been mined, every gold ring, every gold coin, every golden thread came from events like that one. From the deaths of stars so dense that physics breaks down trying to describe their interiors. From objects spinning in the dark, sending out their steady pulses for billions of years before anyone was listening. And here is a question to carry with you, as we continue, one that I find genuinely moving in a quiet way. If the matter in your body was forged in stellar cores and scattered by stellar explosions, and if the heaviest atoms in your body may have been forged in neutron star mergers, then in some sense pulsars are not just cosmic clocks, not just lighthouses in the dark. They are also in a way part of the origin story of the atoms you are made of. You and the pulsars share a history, a deep ancient shared history written in nuclear physics and time. That thought alone, that we are not observers of the cosmos, but participants in it, made from its most dramatic processes, is something worth letting drift through the mind as sleep comes closer. But before sleep arrives completely, there is still more to explore. Because we have talked about what pulsars are made of and how they are born, we have not yet talked about what makes their spin so impossibly hauntingly precise, and why that precision makes them arguably the most useful natural objects in the universe for doing science. A pulsar's tick is not just beautiful, it is a tool, and the story of how we learn to use that tool leads somewhere even more astonishing than where we've already been. Imagine you are holding a ball of clay roughly the size of a basketball, and you set it spinning slowly in your hands. Now imagine compressing that ball, pressing it from all sides simultaneously until it is the size of a marble. What happens to the spin? It doesn't slow down. It doesn't stop. It explodes. The marble spins so fast that if you could see it, it would be a blur. This is conservation of angular momentum, one of the most fundamental laws in all of physics. And it is the reason that a star which rotated lazily over the course of weeks can, after collapsing into a neutron star, spin hundreds of times every second. The law does not negotiate. It does not make exceptions. It simply conserves. Whatever rotational energy existed in the large diffuse object is preserved concentrated in the small dense remnant. And the fastest spinning pulsars we have found push this principle to a place that, even knowing the physics, still feels like it should not be possible. The pulsar designated PSRJ 1748-2446 AD, located in a globular cluster called Terzan 5, about 18,000 light-years from Earth, rotates 716 times per second. 716 complete rotations every single second. A point on its equator, if you could somehow stand there, which you cannot, for reasons we will get to, would be moving at approximately 24% of the speed of light. Not 24 miles per hour, not 2,400 miles per hour. 24% of the speed of light, which is roughly 280 million meters per second. The equator of this object is moving at 71,000 kilometers per second. This is not a metaphor. This is not an approximation. This is what the data shows. The common misconception here is worth addressing directly because it comes up often and it is understandable. Many people, upon hearing about the extreme spin rates of pulsars, assume that the rotation must be gradually slowing, that eventually over a long enough time, a pulsar will simply spin down to a stop. And it is true that pulsars do gradually lose rotational energy, mainly through the radiation they emit. But gradually is doing a lot of work in that sentence. For a young energetic pulsar, the spin-down timescale can be millions of years. For the millisecond pulsars, the fastest ones, which have been spun back up by stealing mass from a companion star, the timescale extends even further to billions of years. We are not watching objects winding down on any human timescale. We are watching objects that are for all practical purposes of a human lifetime eternal. But here is the tension at the heart of the physics. The thing that makes the extreme spin of pulsars not just impressive but physically interesting in a deep way. There is a speed limit, not an arbitrary one, not one imposed by engineering constraints, but one imposed by the laws of physics themselves. A neutron star spinning faster than a certain critical rate would begin to tear itself apart. The centrifugal force at the equator would exceed the gravitational binding force holding the star together, and matter would be flung off into space. Theoretical calculations suggest that the maximum spin rate for a neutron star is somewhere around 1,500 rotations per second, depending on the star's mass and equation of state. The fact that PSRJ 1748-2446 AD spins at 716, roughly half the theoretical maximum, tells us something important. It tells us that neutron stars are not simply spinning as fast as the physics of their formation would suggest. Something shapes the distribution of spin rates. Something sets a ceiling well below the theoretical limit. And understanding what that something is requires understanding not just the neutron star in isolation, but its history, and in many cases, the binary system it lives in. Let us talk about that. Because the story of how a pulsar can spin up from a moderate rotation rate to hundreds of revolutions per second is one of the more elegant processes in stellar astronomy, and it is also a story of intimate gravitational partnership. Many neutron stars do not exist alone. They were born in binary star systems, two stars orbiting each other, and the supernova that created the neutron star did not necessarily destroy the partnership. If the system survived the explosion, the neutron star and its companion star continue to orbit each other. And if the companion star is the right type, particularly if it is a low-mass star that eventually expands into a red giant or begins transferring matter outward, then something extraordinary begins to happen. Matter flowing from the companion star toward the neutron star does not fall straight down. It has angular momentum. It spirals inward, forming a flattened, rotating structure called an accretion disk, a swirling river of gas and plasma that encircles the neutron star and feeds it from the outside. This infalling matter carries angular momentum, and as it is accreted onto the neutron star's surface, it transfers that angular momentum to the star. The neutron star spins up. Gradually, over millions of years of slow, steady accretion, a neutron star that might have been spinning at a modest few rotations per second can be accelerated to hundreds of rotations per second. This is why the fastest spinning pulsars are called recycled pulsars. They have been spun up, re-energized, brought back from a slower, older rotation rate by the patient gravitational gift of a companion star. They are, in a sense, reborn, given a second life faster and brighter than the first, and they are extraordinarily stable. The accretion process that spins them up also tends to bury or restructure their magnetic fields, reducing the energy losses from radiation and allowing them to maintain their spin rates for extraordinarily long periods. Now, let us talk about the magnetic field itself, because it is the other half of what makes a pulsar, rather than simply a fast-spinning neutron star. We touched briefly in an earlier part on the strength of pulsar magnetic fields, but it is worth spending time with the actual physics of what those fields do, because the mechanism by which a pulsar generates its characteristic beams of radiation is not a simple or obvious one, and there are still aspects of it that remain actively debated among physicists. The basic picture is this. The rotating magnetized neutron star creates a rapidly varying electromagnetic field in the space around it. This field accelerates charged particles, electrons, and positrons, mostly to relativistic speeds along the magnetic field lines. As these particles curve along the field lines, they radiate energy in the form of electromagnetic radiation. At the magnetic poles where the field lines converge and the particle energies are highest, this radiation is most intense and it is concentrated into the beam-like structures that we observe as pulses when they sweep past Earth. But the details are enormously complex. The region immediately surrounding the pulsar, called the magnetosphere, is filled with plasma and crossed by magnetic field lines that are simultaneously being dragged around by the star's rotation and trying to maintain their own structure. At a certain distance from the star, called the light cylinder radius, the field lines would need to move at the speed of light to keep up with the rotation which is not permitted. Beyond that radius, field lines open up and particles escape, carrying energy and angular momentum away from the star. This is one of the primary mechanisms by which a pulsar loses rotational energy over time. The precise geometry of how the beam forms, how concentrated it is, at what angles it points relative to the rotation axis, how it evolves as the pulsar ages varies from pulsar to pulsar, and depends on the magnetic field configuration. The age of the star, the details of the particle acceleration, and factors we are still working to understand. This is why not all neutron stars are observable as pulsars from Earth. The beam must sweep across our line of sight for us to detect the pulses. Theoretical estimates suggest that for every pulsar we can observe, there are perhaps 100 neutron stars whose beams point in directions that miss Earth entirely. We are, as always, limited by the direction we happen to be looking. Here is something worth sitting with, a question that has a surprisingly deep answer. Why is the pulse so sharp? Why is the signal we receive not a broad, fuzzy smear of radiation, but a crisp, well-defined pulse that arrives with extraordinary timing, precision? Part of the answer is geometric. The beam is narrow, and as it sweeps past the window of time in which it illuminates Earth is brief. But part of the answer lies in the extraordinary stability of the neutron star itself. Unlike a gas cloud, unlike a planet with weather and geological activity, unlike even the best atomic clocks, which are subject to tiny quantum fluctuations and environmental disturbances, a neutron star is almost perfectly rigid. Its enormous density and the quantum degeneracy pressure supporting it make it extraordinarily resistant to perturbation. When you measure the arrival time of pulses from a millisecond pulsar, you are measuring the rotation of an object hundreds of times more stable than the best human-made timekeepers. The pulse is sharp because the object generating it is, in terms of rotational stability, essentially perfect. This precision is not incidental. It is the foundation of some of the most sophisticated scientific measurements ever made. And it leads directly to a question that occupied physicists for decades and was finally answered not by building a better instrument on Earth, but by watching two pulsars slowly, inexorably spiral toward each other in the dark and measuring what that spiral told us about the nature of space and time itself. That story, the story of the binary pulsar of Russell Hulse and Joseph Taylor, and of the first indirect proof that gravitational waves are real, is one of the most quietly stunning episodes in the history of physics. And it is exactly where we are heading next. In 1974, two astronomers at the Arecibo Observatory in Puerto Rico were doing what astronomers do, pointing a very large dish at the sky and listening. Russell Hulse was a 22-year-old graduate student. Joseph Taylor was his supervisor. They were conducting a systematic survey of pulsars, cataloging the radio pulses arriving from neutron stars scattered across the galaxy, adding new entries to what was then still a relatively young and rapidly growing list of known objects. And then Hulse found something that did not behave the way it should. He had detected a pulsar, a strong, clear periodic signal, arriving with the regularity that pulsars always display. But when he measured the period carefully over successive observations across several days, he noticed something strange. The period was not constant. It was changing. Not randomly, not noisily, it was changing in a smooth, regular, systematic way. The pulses arrived slightly early, then slightly late, then slightly early again, cycling through a pattern that repeated every 7.75 hours. There is only one clean explanation for that kind of systematic variation in a pulsar's period. The pulsar is moving alternately toward us and away from us in a regular orbit. When it moves toward us, the pulses are compressed, slightly arriving with a shorter apparent period. When it moves away, the pulses are stretched, arriving with a slightly longer period. This is the Doppler effect, the same phenomenon that makes a passing ambulance's siren shift pitch as it moves toward and then away from you, applied not to sound, but to the ticks of a cosmic clock. The pulsar designated PSRB 1913 plus 16 was in a binary orbit. It had a companion, and the companion, as subsequent analysis revealed, was another neutron star, dense, dark, and silent, producing no detectable radio emission of its own, but exerting a gravitational pull that bent the pulsar's path through space into an ellipse 7.5 hours for each complete circuit. Two neutron stars, locked in orbit around each other, separated by a distance roughly comparable to the radius of our Sun, meaning the entire system would fit comfortably inside the star we orbit, moving at orbital speeds of hundreds of kilometers per second. And because the pulsar's ticking was so precise, so extraordinarily stable, it functioned as a natural clock of almost unimaginable accuracy, allowing Hulse and Taylor to measure the orbital parameters of the system with a precision that no laboratory instrument on Earth could match. This is where the story takes a turn into something that still produces a quiet sense of awe when you sit with it fully. Albert Einstein's general theory of relativity, published in 1915, predicted that accelerating masses should radiate energy in the form of gravitational waves, ripples in the fabric of space-time itself, propagating outward at the speed of light. The theory was extraordinarily successful in explaining a range of phenomena: the precession of Mercury's orbit, the bending of light around massive objects, the gravitational redshift of light climbing out of a gravity well. But gravitational waves themselves had never been directly detected. The waves produced by any laboratory-scale process were fantastically small, far too small to measure with any technology available in the 20th century. And even the waves produced by astronomical events were expected to be tiny by the time they reached Earth. But there is a consequence of radiating gravitational waves that is, in principle, measurable, even without detecting the waves directly. A binary system that radiates gravitational waves loses energy. As it loses energy, the two objects spiral slowly inward toward each other. The orbital period decreases. The orbit shrinks. If you can measure the orbit with sufficient precision over a long enough baseline, you can determine whether it is shrinking, and if it is shrinking at exactly the rate that general relativity predicts you have. Indirect, but extraordinarily compelling evidence that gravitational waves are real and that Einstein's equations are correct. Hulse and Taylor began measuring. They measured for years. They accumulated data from the Arecibo telescope across decades. Taylor continued the measurements long after Hulse moved on to other work. And what they found published in a series of papers across the 1970s and 1980s was this. The orbital period of PSRB 1913 plus 16 was decreasing. The two neutron stars were spiraling inward. And the rate of that in spiral measured by the cumulative shift in the timing of the pulsar's pulses, plotted against time, matched the prediction of general relativity to within a fraction of a percent. The gravitational wave energy loss, calculated from Einstein's equations, predicted a specific rate of orbital decay. The observed rate matched it, precisely, beautifully, as if the universe had been designed to confirm the theory. In 1993, Russell Hulse and Joseph Taylor were awarded the Nobel Prize in Physics for the discovery of PSRB 1913 plus 16 and the observational evidence it provided for gravitational waves. The Nobel Committee described it as a discovery that has opened up new possibilities for the study of gravitation. Taylor, accepting the prize, remarked that pulsars had become the most perfect clocks in nature and that their perfection was what had made the measurement possible. It is worth pausing here to appreciate the layered elegance of what happened. A naturally occurring object, a dead star, the remnant of a catastrophic explosion spinning in the dark, turned out to be so stable, so precise, so reliable as a timekeeper, that it could be used to test the most profound theory of gravity ever written, with an accuracy that no human-built instrument of that era could approach. The universe, in effect, handed us a laboratory that we could never have constructed ourselves. And the laboratory confirmed with exquisite precision that space and time are not fixed and rigid. They flex and ripple and carry energy in ways that Newton never imagined and that Einstein first described from pure mathematics, sitting at a desk with no data to guide him except the light of his own reasoning. Now, a common point of confusion that is worth clarifying carefully. Many people, upon hearing this story, assume that Hulse and Taylor detected gravitational waves. They did not directly. What they measured was the effect of gravitational wave emission on the orbital evolution of the binary system. The waves themselves, the actual ripples in space-time, were not detected until 2015, when the LIGO interferometers in Louisiana and Washington State registered a signal lasting less than a second, produced by two black holes merging over 1 billion light-years away. That detection event, GW150914, was a different story and a different triumph. Hulse and Taylor's work was the proof of principle, the theoretical bridge, the evidence that made the enormous investment in LIGO scientifically justified. Without the binary pulsar, the case for building LIGO would have been far harder to make. It is one of those cases in science where the indirect evidence was so compelling, so precise, so theoretically clean, that it changed the field before the direct confirmation ever arrived. Scientists had to decide whether to believe it, and the vast majority did, because the numbers were simply too good to be coincidence. Consider what this means for how we think about certainty in science. We often imagine that science requires direct, tangible, eyes-on evidence that you cannot know something until you have held it in your hands or seen it with your own eyes. But the most powerful evidence in science is often indirect. We have never seen an electron. We have never held a quark. We have never visited the core of the sun. And yet we know with extraordinary confidence that these things exist and behave as our theories describe, because the indirect evidence measured carefully matches the predictions with a precision that cannot be accounted for by coincidence. Pulsars gave us that kind of evidence for gravitational waves. And in doing so, they opened a window onto a form of astronomy that had never before existed. Here is a question worth sitting with quietly. If you had to explain to someone, a child or a curious friend with no background in physics, why the slow, steady spiraling of two distant neutron stars toward each other should matter to anyone on Earth, what would you say? What is the human significance of knowing that space itself ripples? The answer, I think, is not primarily practical. It is primarily philosophical. It tells us something about the nature of reality, that the stage on which the universe plays out its drama is not fixed and passive, but dynamic and responsive. That mass and energy do not just sit in space, they curve, ripple, carry information through it at the speed of light. That the universe is not a theater, but a participant. And pulsars, those spinning, pulsing, patient timekeepers in the dark, were the instruments that first let us hear the universe's own motion, translated into something we could measure. The Hulse-Taylor pulsar is still being monitored today. Decades of continued timing observations have refined the orbital parameters to extraordinary precision. The accumulated shift in the pulsar's timing, relative to what it would be if the orbit were not decaying, now amounts to more than 40 seconds, a number that grows by roughly 76 microseconds per year as the orbit shrinks. The two neutron stars are predicted to merge in approximately 300 million years. When they do, they will produce a gravitational wave burst, and almost certainly a kilonova, a flash of heavy element synthesis of the kind we discussed earlier, forging gold and platinum and other heavy elements and scattering them into the galaxy, an ending that is also a beginning, a death that creates. We have now traveled from the first detection of a pulsar by a graduate student reading chart paper through the physics of what a pulsar is, through the extraordinary internal structure of neutron stars, through the mechanics of how they spin, and now to the moment when two of them locked in each other's gravity gave us the first proof of gravitational waves. Each of these threads is remarkable on its own. Together, they form something larger, a portrait of objects that are simultaneously the most extreme environments in the known universe and the most precise scientific instruments nature has ever produced. But we have not yet talked about precision in its most practical sense. We have not yet talked about what happens when astronomers take the extraordinary timekeeping ability of millisecond pulsars and apply it not to testing Einstein, but to navigating the cosmos, to building from the ticking of dead stars, something that functions as a GPS system for the entire galaxy. That idea pulsar timing arrays, and the possibility of interstellar navigation, is quieter than gravitational waves, less dramatic in its origins, but in its implications perhaps the most far-reaching application of pulsar science that exists. And it leads somewhere that no one in 1967 could possibly have anticipated. Picture this: you are lost at sea. No landmarks, no coast visible in any direction. The stars are above you, clear and cold, and in your hand you hold something extraordinary, a list of lighthouses. Not just any lighthouses that never go dark, never flicker, never shift position, and each one pulses at a frequency so precise that simply by measuring how long it takes for that pulse to reach you and how that timing changes as you move, you can determine exactly where you are in the ocean, down to the meter, without a satellite, without any technology built by human hands. Just the lighthouses, ancient, steady, faithful, and mathematics. This is not a metaphor for something romantic and abstract. This is in precise technical terms what astronomers have proposed doing across the scale of the entire galaxy, using pulsars as navigational beacons, using their ticking as reference points in a galactic coordinate system that requires no infrastructure, no maintenance, no power supply, and no human upkeep. A GPS system written not in silicon and software, but but in the physics of collapsed stars, broadcasting freely in all directions, waiting to be used by anyone or anything, with the instruments to receive it and the mathematics to interpret it. The idea has a name: pulsar timing arrays. And what they have already accomplished and what they are beginning to reveal about the universe at the largest scales is one of the quietest, most profound developments in modern astronomy, something that most people have never heard of, but that may in the coming decades transform our understanding of the cosmos as profoundly as the first detection of gravitational waves. Let us begin with the concept itself, because it is more elegant than it might initially sound. A pulsar timing array, PTA in the shorthand, is a network of radio telescopes distributed around the Earth, all monitoring the same set of carefully chosen millisecond pulsars simultaneously and continuously. Each pulsar in the array functions as an extraordinarily precise clock. Each one sends out pulses at a rate so stable that over years and decades, the accumulated timing of those pulses can be predicted to fractions of a microsecond. If something perturbs the timing, if pulses arrive consistently slightly early or slightly late, or if the pattern of early and late arrivals correlates across multiple pulsars in specific ways, that perturbation carries information. It is a signal, and the particular kind of signal that pulsar timing arrays were designed to detect is something that stretches and compresses the very fabric of space-time, a background of gravitational waves rippling through the universe at the lowest frequencies imaginable. Here is the distinction that matters. The gravitational waves detected by LIGO, the ones produced by merging black holes and neutron stars, are high-frequency waves, short wavelengths, fractions of a second in period. LIGO's mirrors oscillate in response to them, moving by distances smaller than 1,000th of the diameter of a proton. To detect them, you need precision interferometers isolated from vibration, cooled to near absolute zero, with arms 4 kilometers long. And even then, the signal lasts for less than a second. The gravitational waves that pulsar timing arrays are designed to detect are at the opposite extreme. Their periods are not fractions of a second, they are years, decades. Their wavelengths are measured in light years. These are the lowest frequency gravitational waves in the universe, produced not by individual mergers, but by something far more diffuse and pervasive: the accumulated gravitational wave emission of every supermassive black hole, binary pairs of black holes, each millions or billions of times the mass of the Sun, orbiting each other at the centers of merging galaxies across the entire observable universe. These waves, if they exist as predicted, do not sweep through a detector and vanish in under a second. They fill the universe, continuously overlapping and combining into what physicists call the stochastic gravitational wave background, a gentle, permanent, omnidirectional trembling of space-time itself. The universe at the largest scales is humming, and the only instruments sensitive enough to hear that hum are arrays of millisecond pulsars monitored for years, their timing analyzed for the specific correlated patterns that a gravitational wave background would produce. In June 2023, 4 major pulsar timing array collaborations, the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, the European Pulsar Timing Array, the Indian Pulsar Timing Array, and the Chinese Pulsar Timing Array simultaneously announced evidence for exactly this signal. The announcements were coordinated, and the data were consistent across all 4 independent data sets. After 15 years of patient observation, the gravitational wave background appeared to have been detected. Not confirmed definitively, the statistical evidence was compelling, but not yet at the threshold physicists call 5 sigma, the gold standard for a definitive detection, but strong enough that the community sat up and the headlines followed. What the collaborations observed was a pattern of correlated timing, residuals across the pulsars in their arrays, small systematic deviations from predicted arrival times that followed a specific mathematical signature. The signature is called the Hellings-Downs curve, named after the physicists who calculated in 1983 what the angular correlation between pulsars should look like if a gravitational wave background were present. Pulsars separated by 90 degrees in the sky should show a specific correlation. Pulsars separated by other angles should show different predictable correlations. The observed data match the Hellings-Downs curve. Imperfectly, there are still questions about the strength and spectral shape of the signal, but the match was there. The universe's hum carried in the ticking of dead stars appears to have been heard. There is a common misconception worth addressing here because the 2023 announcement generated some confusion in popular media. Several headlines describe this as the detection of gravitational waves from supermassive black hole mergers. That is somewhat misleading. What was detected, if the signal holds up under further analysis, is not waves from a specific event or a specific source. It is the combined blended signal from an enormous number of supermassive black hole binaries spread across billions of light years and billions of years of cosmic history. It is, in effect, the background noise of the universe's largest gravitational machines, all humming at once, producing a cosmic chorus that has been washing through the galaxy, through our solar system, through the Earth, through each of us for the entire history of life on this planet. We have been swimming in gravitational waves this entire time. We simply did not have the instruments to notice. Now, alongside the cosmic ambition of the gravitational wave background, search pulsar timing arrays have a more immediately practical application, one that sits closer to the navigational metaphor we began with. The NICER telescope, which we mentioned in an earlier part of this journey, demonstrated that precise X-ray timing of pulsars can determine a spacecraft's position in deep space without relying on Earth-based tracking. In 2018, NICER conducted the first in-space demonstration of X-ray pulsar navigation, sending signals between the telescope and the pulsar PSRB 0531 plus 21, the Crab pulsar, and using the timing of those signals to determine the spacecraft's position to within roughly 16 kilometers. 16 kilometers in the vastness of space using a dead star 6,500 light-years away as a reference beacon. This is not a minor technical achievement. It is a proof of concept for something that, as humanity ventures further into the solar system and eventually beyond, could become as foundational as GPS is to navigation on Earth today. Future deep space missions to the outer planets to nearby star systems, if such voyages ever become possible, would not be able to rely on Earth-based tracking. The signal delay from Earth grows too long, the pointing precision required becomes too demanding. But pulsars are everywhere. They broadcast continuously. They require nothing from us. A spacecraft equipped with an X-ray telescope and the right software could use them to know at any point in its journey exactly where it is in the solar system or in principle in the galaxy. Carl Sagan understood this decades before the technology to make it practical existed. In 1972 and 1973, the Pioneer 10 and Pioneer 11 spacecraft were launched toward the outer solar system, each carrying a gold anodized aluminum plaque designed by Sagan and Frank Drake. On that plaque, among the figures of a man and woman and a diagram of the hydrogen atom, was a pulsar map, 14 lines radiating from a central point, each representing the direction and relative period of a known pulsar with the sun at the center. It was, as Sagan described it, a return address, a way for any civilization that might encounter the spacecraft hundreds of thousands or millions of years from now to determine when and where in the galaxy it originated. The pulsars would serve as reference points, objects whose periods change predictably over time, allowing a sufficiently sophisticated recipient to calculate from the periods encoded on the plaque and the periods of those same pulsars when the spacecraft is found approximately when it was launched. Sagan chose pulsars because they are the most recognizable, most universal, most unambiguous landmarks in the galaxy. Any civilization advanced enough to detect radio waves and build telescopes would know pulsars, would have cataloged them, would recognize a pulsar map for what it is. He understood intuitively what has taken the scientific community decades to fully articulate, that pulsars are not just objects of astronomical interest. They are landmarks of the cosmos. Navigation aids written in physics available to anyone with the instruments and the patience to listen. Here is the thought that lingers with me when I sit with all of this, and I offer it to you now gently as the narrative drifts toward the next part of the journey. We have, in the course of human history, built many systems of navigation: stars, magnetic compasses, paper charts, radar, GPS satellites. Each one was the product of human ingenuity, human resources, human labor. Each one can fail, can be jammed, can decay, can become obsolete. But pulsars require none of that. They existed before any of our navigational systems were conceived. They will continue to exist long after every GPS satellite has decayed out of orbit and every chart has turned to dust. They are, in the deepest sense, permanent fixtures of the galaxy, at least on any time scale that matters to us. And yet, as permanent and reliable as pulsars appear, there are moments when they surprise us. Moments when the universe's most faithful timekeepers do something unexpected. Something that, when it was first observed, left astronomers puzzled for years. And in that puzzle lay a discovery about the interior of neutron stars, about quantum physics operating at scales of kilometers rather than nanometers that no one had anticipated. A pulsar on occasion will suddenly spin faster, not gradually, suddenly, in a fraction of a second, and then slowly relax back toward its previous rate. Astronomers call this a glitch, and the explanation for why it happens is one of the most unusual and quietly beautiful stories in all of physics. That is where we head next, into the interior of the neutron star, where quantum mechanics operates at the scale of mountains, and where the rules of ordinary matter simply cease to apply. On February 24th, 2,000 astronomers monitoring a pulsar called PSRJ 0537-6910, located in the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way, noticed something that should not have happened. The pulsar glitched. In a fraction of a second, without warning, without any detectable external trigger, the rotation rate of this neutron star increased. Not by much. The fractional change in spin frequency was roughly 1 part in a million. But 1 part in a million for an object rotating 62 times per second is a measurable, unambiguous, physically significant jump. The pulsar that had been ticking with the faithfulness of the finest clock in the known universe suddenly skipped, lurched forward as if something deep inside had shifted and released. Then, over the following days and weeks, the pulsar's spin rate relaxed back toward its previous value, slowly, incompletely, leaving the star spinning slightly faster than it had been before, the event on a new trajectory that would itself eventually be interrupted by the next glitch. PSRJ 0537-6910 is, by the way, the most frequently glitching pulsar known. It glitches roughly every 100 days, which, in pulsar terms, is extraordinarily restless. It is as if this particular dead star cannot quite settle into stillness. Glitches were first discovered in 1969, just 2 years after the initial detection of pulsars. 2 pulsars, the Vela pulsar and the Crab pulsar, were observed to suddenly speed up, and the community immediately recognized that this was not noise, not measurement error, but a real physical event. The question was, what causes it? And the answer arrived at, after years of theoretical work and refined through decades of observation, is one of those explanations that sounds on first encounter almost too strange to be true, and yet is grounded in quantum mechanics, so well established that the physics community accepts it with confidence. The explanation requires us to go back inside the neutron star, into the layer we touched on briefly in an earlier part of this journey, the region of superfluid neutrons beneath the solid crust. Superfluidity is a quantum phenomenon. It occurs in certain materials at extremely low temperatures, when quantum effects begin to dominate over thermal randomness and particles enter collective coherent quantum states. In a superfluid, the fluid flows without any viscosity, without any internal friction whatsoever. A superfluid set spinning in a container will, if the container is held still, continue spinning indefinitely, not approximately indefinitely. Actually, indefinitely at least, until something disturbs the quantum state. This has been demonstrated in laboratory experiments with liquid helium cooled to near absolute zero. The helium climbs the walls of its container, defying ordinary intuition about how liquids behave, flowing without resistance, without dissipation, in a state governed by quantum coherence rather than classical mechanics. Inside a neutron star, the density and pressure conditions are such that neutrons in the inner crust and outer core are expected to form a superfluid, not a small laboratory-scale superfluid, a superfluid that extends across kilometers of neutron star interior, a quantum fluid on an astronomical scale. Here is where the physics of glitches comes in, and it requires one more concept: quantized vortices. In a rotating superfluid, the rotation cannot be distributed smoothly throughout the fluid the way it would be in a normal viscous liquid. Instead, the rotation organizes itself into discrete thread-like structures called vortices lines, around which the fluid circulates, each carrying a fixed quantized amount of angular momentum. The faster the superfluid rotates, the more vortices it contains. The vortices are real physical structures. They have been directly observed in laboratory superfluids, and they interact with each other and with the surrounding material in ways that can be calculated and modeled. In a neutron star, these superfluid vortices are believed to become pinned, attached, anchored to the crystalline lattice of the neutron star's crust. This is the key to understanding glitches. As the pulsar spins down gradually due to electromagnetic radiation, losses the solid crust slows, but the superfluid interior with its vortices pinned to the crust cannot slow in the same smooth way. The vortices accumulate stress. Angular momentum builds up in the superfluid, unable to transfer to the crust because the vortices are pinned. The system stores rotational energy like a coiled spring building tension over months or years. And then suddenly something, perhaps a starquake in the crust, perhaps a critical threshold of vortex stress, triggers a sudden catastrophic unpinning of a large number of vortices simultaneously. They break free. Angular momentum transfers from the superfluid to the crust in a fraction of a second. The crust speeds up, the pulsar glitches, and then over the following days and weeks, the vortices repin, the system relaxes, and the long, slow spin-down resumes until the next glitch. This explanation in the superfluid vortex unpinning model is the leading theoretical framework for pulsar glitches. It is not proven beyond all doubt. There are details that remain contested, and alternative models that explain some observations better than others. But the broad picture is widely accepted, and what makes it remarkable is this: pulsar glitches give us observational access to superfluid behavior in a regime of density and pressure that no laboratory can recreate. Every time a pulsar glitches, it is in effect running an experiment on the quantum properties of ultra-dense matter and broadcasting the results across the galaxy. We are reading the data from experiments conducted at densities 12 orders of magnitude beyond anything achievable on Earth, powered by the quantum mechanics of matter, under conditions that exist nowhere else in the observable universe. Now glitches are unusual but not rare. Hundreds have been cataloged across dozens of pulsars. But there is a far more extreme class of neutron star behavior, one that makes glitches look modest, and it comes from a subtype of neutron star that occupies its own category at the edge of what physics allows: magnetars. We mentioned magnators briefly in an earlier part of this journey, but they deserve their full moment here, because the events they produce are among the most energetic individual phenomena in the known universe. And at least one of those events directly affected planet Earth in a way that is both measurable and unsettling to contemplate. A magnetar is a neutron star with an exceptionally powerful magnetic field, fields estimated at 10 to the power of 15 Gauss, or roughly 1,000 times stronger than the already extraordinary fields of typical pulsars. For context, the Earth's magnetic field is roughly half a Gauss. A refrigerator magnet is perhaps 100 Gauss. The strongest continuous magnetic fields ever produced in a laboratory are around 45 Tesla, or 450,000 Gauss. A magnetar's field is approximately 10 billion times stronger than that. It is not just the strongest magnetic field in the universe, it is stronger than anything that can exist in ordinary matter. Because at that field strength, the magnetic energy density exceeds the energy density of a proton's rest mass, and the physics of atoms as we know them breaks down. At those field strengths, something called vacuum birefringence is predicted. The quantum vacuum itself, normally perfectly uniform in its optical properties, becomes anisotropic. Light traveling through the region near a magnetar is expected to behave differently, depending on its polarization direction, because the magnetic field is so strong, it polarizes the vacuum. This has recently received tentative observational support from the neutron star RxJ 1856. 5-3754, where X-ray polarization measurements published in 2017 showed hints of the effect. If confirmed, it would be the first direct observational evidence of quantum electrodynamic effects in the vacuum, physics predicted theoretically, but never directly seen in a laboratory. But the most dramatic things magnetars do are their bursts and flares. Magnetars are not steady, reliable pulsars in the way their less magnetically extreme cousins are. They are volatile. Their magnetic fields are so strong that they can cause the solid crust of the neutron star. Remember a crust made of densely packed atomic nuclei in a crystalline lattice extraordinarily rigid by ordinary standards to crack and shift. These starquakes release magnetic energy in sudden intense bursts of gamma rays and X-rays lasting anywhere from fractions of a second to minutes, with luminosities that can briefly exceed the output of hundreds of billions of ordinary stars. On December 27, 2004, one of these events occurred, and it was close enough to matter. The magnetar SGR 1806-2, located approximately 50,000 light-years away in the constellation. Sagittarius released a giant flare. In a burst lasting approximately 0.2 of a second, it released more energy than our Sun emits across 250,000 years. The initial spike of gamma radiation, the most intense burst of gamma rays ever detected from outside our solar system, struck Earth at 21:30:26 UTC. And despite being 50,000 light-years away, nearly halfway across the Milky Way, the energy was sufficient to ionize the upper atmosphere of Earth, specifically the ionosphere, the layer of electrically charged particles at altitudes of roughly 60 to 90 kilometers that reflects radio waves and is essential for long-distance radio communication. For approximately 0.2 of a second, the ionosphere of the night side of Earth was disturbed. Radio signals in certain frequency ranges were briefly disrupted. The disturbance was detected by satellites monitoring the gamma-ray burst and by ground-based instruments monitoring atmospheric ionization. It was, in terms of direct physical effect on our planet, the most significant impact from any astronomical event in recorded history. More immediate than any supernova, more measurable than any other gamma-ray burst. And the source was 50,000 light-years away. Consider what that means. The event that caused it occurred at a distance so vast that light traveling at nearly 300,000 kilometers per second took 50,000 years to cross it. And yet, the energy released in that fraction of a second was sufficient to physically alter Earth's atmosphere. Had the magnetar been significantly closer, within a few thousand light-years, say the event could have been catastrophic. At distances of a few hundred light-years, a magnetar flare of comparable intensity could potentially strip away atmospheric ozone and expose the surface to dangerous levels of radiation. There are no known magnetars within dangerous range of Earth. The closest known examples are thousands of light years away. But the December 27, 2004 event is a reminder that the universe is not always the quiet, patient, contemplative thing that pulsars and their steady rhythm tend to suggest. Beneath the faithfulness of the cosmic heartbeat, there are moments of violence on scales that are genuinely difficult to absorb. Moments when a dead star tens of thousands of light years away reaches out and touches the atmosphere of a living world. Here is a question worth turning over gently as this part draws toward its close, not a frightening question, just an honest one. We tend to think of threats to Earth as coming from within the solar system, from asteroids, from volcanic activity, from the slow changes of climate and geology. But the universe has its own agenda operating on scales of distance and energy that dwarf anything in our immediate neighborhood. A magnet or flare 50,000 light years away. A supernova close enough to bathe Earth in X-rays. A gamma ray burst aimed by cosmic chance in our direction. These events are rare. On any human timescale, they are essentially impossible. But the universe is old and vast, and the tally of things it is capable of is longer than any catalog we have compiled. What pulsars offer in the face of all of this is something quietly reassuring. In all the violence of stellar death, in all the extremity of neutron star physics, the product that endures is regularity, steadiness, a pulse that keeps time through billions of years of cosmic change. The universe makes catastrophes, yes, but it also makes clocks, and those clocks somehow are more enduring than the catastrophes that created them. What that steadiness has enabled the science it has unlocked, the navigation it makes possible, and the message it sent across the cosmos, even before we discovered it existed, is where the final chapters of tonight's journey now lead. In the summer of 1977, two spacecraft left Earth within weeks of each other, carried on trajectories calculated by scientists who knew with certainty that neither probe would ever return. Voyager 1 and Voyager 2 were designed to do something no human-made object had ever done, to travel past the outer planets of the solar system, in a grand tour made possible by a rare alignment of the planets that would not repeat for another 175 years, and then to keep going, past Neptune, past the heliopause, the boundary where the sun's influence on the surrounding interstellar medium finally fades, into the space between stars, into a silence so deep and so vast that no signal, however powerful, could reliably bridge it. Each spacecraft carried a golden record, not a record intended for humans who might recover the probe. The trajectories made recovery impossible. The records were intended for whoever or whatever might encounter the spacecraft after a journey of tens of thousands of years through interstellar space. They carried sounds of Earth music language, the sound of rain and wind and ocean. They carried images. And on each record's protective cover, etched in gold, was something quietly extraordinary, a map, a star map, but not a map that used the stars as landmarks in the way that ancient navigators use them, by apparent position in the sky. This map used something more precise, more universal, more timeless than the positions of stars. It used pulsars. 14 lines radiated outward from a central point on the cover, each line representing the direction from Earth to a known pulsar with the length of the line encoding the pulsar's period. Its rotational frequency expressed in binary notation using the spin-flip frequency of the hydrogen atom as the base unit of time, a value that any technologically advanced civilization would recognize and could use as a reference. At the end of each line, a short binary number encoded the period of that pulsar at the time of the spacecraft's launch. Carl Sagan, who conceived the message with Frank Drake and Linda Salzman. Sagan chose pulsars deliberately and thoughtfully. A pulsar is, he argued, the most recognizable object in the galaxy, a natural radio source pulsing at a specific stable, measurable frequency, identifiable by its period and its position in the sky. Any civilization advanced enough to build radio telescopes would have cataloged the pulsars, would know where they are, would be able to look at the map, identify the 14 pulsars from their encoded periods, find the intersection of their directions. and determined this spacecraft came from here, from this star, at this location in the galaxy. And because pulsar periods change predictably as the pulsars spin down over time from approximately this moment in cosmic history, the pulsar map is in effect a return address written in the language of physics, a language with no cultural assumptions, no human conventions, no dependence on shared history or shared alphabet, a language that any sufficiently advanced mind in the universe could in principle read. Sagan understood that if we were ever to communicate our existence and our location to minds we had never met and could not anticipate, we would need a vocabulary that required no translation, and that the most universal vocabulary available to us was mathematics written in the behavior of the most recognizable objects in the cosmos. There is a common point of debate around this decision that is worth addressing because it has become more prominent in recent decades. Some scientists, most notably Stephen Hawking, in his later years, argued that broadcasting the location of Earth to unknown civilizations is potentially dangerous, that any civilization capable of detecting and acting on the Voyager message would be sufficiently advanced to pose a threat, and that the history of contact between technologically unequal civilizations on Earth gives reason for caution. Others argue that the signals humanity has already broadcast decades of television and radio transmissions, radar pulses. The electromagnetic signature of a technological civilization have already advertised our existence to any sufficiently sensitive receiver within roughly 100 light years, that the Voyager records add nothing meaningfully new to our detectability, while adding something profoundly meaningful to the gesture. This is not a debate with a clean resolution. It is a genuine ethical question at the intersection of science philosophy and the long arc of human civilization. What do you think? If you had been advising Sagan in 1977, would you have included the pulsar map? But set aside for now the question of interstellar communication, because the practical application of pulsars to navigation, the idea that was embedded symbolically in the Voyager message, has, in recent years, moved from metaphor to engineering, and the trajectory of that development points towards something that may matter enormously for the future of human space exploration. The fundamental problem with navigating in deep space is one of reference. On Earth, GPS works because there are satellites in known orbits broadcasting precise timing signals, and a receiver can determine its position by triangulating the signals from multiple satellites. In the inner solar system, spacecraft can be tracked from Earth using the Deep Space Network, a system of large radio antennas that send ranging signals to spacecraft and measure the round-trip time to determine distance and velocity. This works adequately for missions to the planets, but it has limitations. The signal delay from Earth to a spacecraft at Neptune is roughly 4 hours one way. Any mission that needs to react to its environment in real time, landing on a body with uncertain terrain, navigating through a debris field, making rapid orbital adjustments, cannot wait 8 hours for a round-trip signal. The spacecraft must navigate autonomously. This is where pulsar-based navigation becomes not a romantic idea, but a practical engineering solution. A spacecraft equipped with an X-ray telescope pointed at a set of known millisecond pulsars can, in principle, measure the arrival times of X-ray pulses from multiple pulsars simultaneously. Because the timing of those pulses is known to extraordinary precision, and because the timing shifts predictably as the spacecraft moves through the solar system in ways governed by the geometry of the spacecraft's position relative to Earth and the pulsars the spacecraft can solve for its own position using the pulsar timing data alone without any signal from Earth. This is not hypothetical. The NICER telescope, the Neutron Star Interior Composition Explorer, was launched to the International Space Station in 2017. And in 2018, it conducted the first demonstration of X-ray pulsar navigation in space. The system, called Sextant Station Explorer for X-ray timing and navigation technology, used timing data from the Crab pulsar and other bright X-ray pulsars to determine the position of the ISS to within approximately 16 kilometers. 16 kilometers in space, where spacecraft frequently have position uncertainties of hundreds or even thousands of kilometers without active tracking. And this was a first demonstration with instruments not fully optimized for navigation. The potential accuracy of a purpose-built system is considerably better. NASA and the European Space Agency have both conducted studies on the feasibility of pulsar navigation for future deep space missions. A dedicated X-ray pulsar navigation system, lightweight, autonomous, requiring no communication with Earth, could guide a spacecraft from Earth to Mars, or to the outer solar system, or beyond, using only the ticking of dead stars as its reference. The system would never lose signal. It would never be jammed. It would work equally well at any point in the solar system, and potentially at any point within the galaxy, reachable by future generations of spacecraft. Its accuracy would improve as our knowledge of pulsar timing improves, and the global network of pulsar timing arrays, which we discussed in an earlier part of this journey, is continuously refining the ephemerides of hundreds of millisecond pulsars to the precision needed for navigation. There is something quietly poetic about this. Carl Sagan put a pulsar map on the Voyager spacecraft as a message to the universe, a symbolic use of pulsars as cosmic landmarks. Less than half a century later, engineers are building systems that use pulsars as literal navigation aids for spacecraft, transforming the symbol into a practical tool. The idea preceded the technology by decades, and the technology is now catching up to the vision. But pulsars offer something to future explorers beyond simple position fixing. They offer time. And in the context of deep space missions, time is almost as important as position. The clocks aboard spacecraft drift over time. Not by much. Modern crystal oscillators and atomic clocks are extraordinarily stable. But no clock is perfect, and over the months and years of a deep space mission, even small drifts accumulate. A clock that is off by 1 microsecond per day will have drifted by more than a minute over a 2-year mission. For navigation purposes, timing errors translate directly into position. Errors. A 1 microsecond timing error corresponds to a roughly 300-meter position error, since light travels 300 meters in a microsecond. Millisecond pulsars, with their extraordinary timing stability, can serve as absolute time references for a spacecraft clock. By comparing the spacecraft's clock to the arrival times of pulsar pulses, which are known from Earth-based timing, to fractional microsecond accuracy, the spacecraft can detect and correct its own clock drift autonomously. No communication with Earth required. The dead stars of the galaxy ticking faithfully in the dark become the timekeepers for the living beings who venture out among them. Here is what strikes me most about this, and what I think is worth carrying into the quieter reflections that close this part of the journey. We have a tendency as a civilization to think of our technological achievements as separating us from nature, as human additions to a universe that is indifferent to our purposes. We build our clocks, our satellites, our communication systems, our navigation infrastructure. We create the tools that we need. But in the case of pulsars, something different is happening. The universe has already built the infrastructure. The navigation network already exists, scattered across the galaxy in the form of spinning dead stars, pulsing faithfully at frequencies stable enough to guide anything that can measure them. We did not build it. We did not plan it. It was here long before we arrived, and it will be here long after everything we have built has decayed and gone dark. Our only contribution, the only thing that was required of us, was to notice, to listen, to learn the language that the universe was already speaking. And perhaps that is the deepest lesson in the long layered story of pulsars. Not that the cosmos is indifferent, not that nature is hostile, not that the universe is a cold and empty place, but that it is already in ways we are still discovering astonishingly useful to the creatures who pay close enough attention. The instruments we need were already there. The clocks were already running. The beacons were already lit. We had only to open our eyes, or rather our telescopes, and look. That thought that the universe was already, in some sense, waiting for us to learn to read it carries us now into the final part of tonight's journey, where we pull all these threads together not to tie them into a neat conclusion, but to let them drift and breathe and settle the way the mind does in the last quiet moments before sleep finds it. We began tonight with a hand on a chest, with the simplest, most intimate thing a human being can feel, the quiet percussion of a living heart, beating without instruction, without effort, without any conscious demand from the mind that houses it. Steady, patient, faithful. And now, after traveling through the deaths of stars and the births of pulsars, through the chart paper of a graduate student in Cambridge and the Nobel Prize that went to the wrong person, through supernovae and neutron superfluids and magnetar flares that reached across 50,000 light-years to touch the atmosphere of our world, through binary orbits that proved Einstein right, and gravitational waves that hum through the fabric of space. After all of that, we return to the heartbeat, because that is what pulsars are at their deepest level, not machines, not accidents, not merely useful. They are the heartbeat of a universe that has been alive in its own strange way far longer than life itself has existed on this planet. And the fact that we, these brief and improbable creatures on a small blue world, in an unremarkable corner of a spiral galaxy, have learned to hear, that heartbeat, have learned to decode it, to use it to be moved by it, is, I think, one of the most quietly extraordinary things our species has ever done. Let us spend these last few minutes not in the machinery of neutron stars, but in the meaning of the whole. There are currently, as of the most recent catalogs, roughly 3,400 known pulsars in the Milky Way. 3,400 individual dead stars, each spinning, each sending out its beam, each ticking with a precision that shames our finest instruments. Astronomers estimate that the actual number of neutron stars in our galaxy, the vast majority of which are not oriented to sweep their beams past Earth and thus remain invisible to us, is somewhere between 100 million and 1 billion. 1 billion dead stellar cores scattered across the galaxy, spinning quietly in the dark. Most of them undetected, most of them known to no one. Their pulses sweeping through space in directions that, by the accident of geometry, have never intersected a telescope pointed by curious hands. There is something in that number that I find both humbling and strangely comforting. The universe is vastly more populated with these objects than our observational record suggests. For every pulsar we know, every one we have named, cataloged, timed, studied, argued about, there are perhaps 10,000 more that we have never seen. The galaxy is full of heartbeats we have not yet learned to hear. And the ones we have found, what have they given us? They gave us the first proof that stars can collapse into objects of almost unimaginable density, validating theoretical predictions that had seemed until 1967 to be pure speculation. They gave us the first indirect evidence for gravitational waves opening a window onto a form of astronomy that Einstein predicted but could not confirm. They gave us the first hints of a gravitational wave background humming through the cosmos, the accumulated voices of a billion supermassive black hole binaries spread across the observable universe, whispering through the fabric of space-time in frequencies measured not in kilohertz, but in nanohertz in cycles per year, in rhythms so slow that we needed decades of observation to begin to hear them. They gave us a navigational system that requires no human infrastructure, no power supply, no maintenance, a network of beacons built by physics and available to any civilization advanced enough to listen. And they gave us a window into the interior of matter at densities that no laboratory can recreate, a window into quantum fluids the size of cities, into magnetic fields that warp the vacuum itself, into physics that sits at the boundary between the known and the genuinely mysterious. All of this from objects that are, by the standards of the cosmos, tiny, 20 kilometers across, the size of a city, smaller than the island of Manhattan, objects so small and so dense and so far away that they appear even in our most powerful telescopes as dimensionless points of light, or more often as pure radio signals, invisible to the eye, detectable only by the patient accumulation of data across months and years of careful listening. The lesson of pulsars. If we are allowed to extract a lesson from a cosmic object, which perhaps we always are, is the lesson of attention, of what becomes visible when you slow down and look carefully at things that seem too small or too regular or too strange to bother with. Jocelyn Bell looked at squiggles on a paper chart and saw the first pulsar. Russell Hulse looked at a slightly irregular period and found a binary neutron star system that would prove Einstein right. Taylor and his colleagues looked at decades of accumulated timing data and heard the universe losing energy to gravitational waves. In 2023, astronomers looked at 15 years of millisecond pulsar timing and found the background hum of the cosmos. None of these discoveries were made by looking harder at the obvious. All of them were made by paying attention to something that could easily have been dismissed, something that a less curious mind, a less patient observer, a less stubborn scientist would have set aside and moved on from. The history of pulsar astronomy is at its core a history of people refusing to look away. And here is the thought that I want to leave with you drifting gently as sleep approaches. We live in a world that moves very fast. That rewards speed and volume and the appearance of certainty. That sometimes makes patience feel like inefficiency and quiet observation feel like passivity. But pulsars, those spinning, faithful ancient timekeepers, embody a different way of being present in the universe. They do not try to be noticed. They simply pulse. They simply tick. They have been doing it for millions or billions of years, and they will keep doing it long after anything we have ever built has dissolved back into the matter it came from. The Crab pulsar born from the supernova that Chinese and Japanese astronomers recorded in 1054, the guest star that blazed in daylight for 3 weeks, is still spinning 33 times per second tonight. It was spinning 33 times per second last night and the night before, and every night for the 971 years since the explosion was first seen from Earth. It will be spinning 33 times per second on the night when our sun first begins to expand into a red giant, roughly 5 billion years from now. On the night when the last red dwarf in the Milky Way finally exhausts its fuel and fades perhaps 100 trillion years from now, there will still be neutron stars spinning somewhere in the dark, slowing now, very slowly over unimaginable timescales, but still spinning, still faithful, still sending out their pulses into a universe that may by then contain no one left to receive them. And maybe that is the most honest, most quietly moving thing about pulsars. Their faithfulness does not depend on an audience. They do not pulse because we are listening. They pulse because the physics demands it, because angular momentum must be conserved, because magnetic fields must radiate, because the laws of the universe apply, whether or not there is anyone around to observe them being applied. The heartbeat was beating before we evolved. It will keep beating after we are gone. We were privileged for a brief window of cosmic time to listen. Here is a question I want to leave with you. Not a scientific one, but a personal one. The kind that sometimes surfaces in the space between wakefulness and sleep. What would it mean to you in your own life to be that reliable, that patient, to find one thing, one true, clear, faithful thing, and simply do it? Not for recognition, not because someone is watching, but because the physics of who you are demands it. Pulsars do not choose to pulse, but perhaps there is still something worth borrowing from them. A model of steadiness, of showing up, of sending out your signal into the dark even when you cannot know whether anyone is receiving it. The universe, it turns out, noticed Jocelyn Bell's squiggly chart paper eventually. It noticed the binary pulsar's slow decay eventually. It noticed the hum of gravitational waves eventually. Patience in the cosmos is never truly wasted. Tonight you have traveled through one of the most extraordinary stories in all of science. You have met the objects that are simultaneously the densest, the fastest rotating, the most precisely timed, and in many ways the most scientifically productive things in the observable universe. You have heard the story of a discovery made by a graduate student who was told her finding was probably interference. You have felt, I hope, something of the scale and strangeness and beauty of a cosmos that makes catastrophes and clocks with equal facility, that builds navigation systems from dead stars, that whispers through space-time in frequencies it takes 15 years of listening to begin to hear. And now, as the thoughts settle and the breath slows and the room grows quieter around you, I want to say genuinely without formality, thank you. Thank you for spending this time here in this quiet space between the known and the imagined. Thank you for being curious enough to keep listening. Thank you for being the kind of person who lies awake some nights and wonders what else is out there spinning in the dark, sending out its signal patient and faithful and unimaginably old. The universe is vast, and most of it has never been named. But you named a little of it tonight by paying attention to it, by letting it matter. Sleep well. Dream of something steady and ancient and good. And know that somewhere right now, a dead star is spinning 33 times per second, or 62, or 716, sending its pulse across the galaxy, faithful as a heartbeat, quiet as the space between stars. It was here before us. It will be here after. And for a little while tonight we listened. Good night. We have so many more quiet journeys ahead, through black holes and ocean worlds, through ancient extinctions and the chemistry of life, through the deepest caves on Earth and the outermost edges of what telescopes can see. Each story waiting to be told softly in the dark to anyone willing to slow down and listen. Stay close. The next story is not far away.